Okay, this is the last part of 4.1 through 4.3. We're going to tack on some applications to what we've learned so far in this chapter. So as we talk about degrees, we're going to look at something else that we can do with these, which is to break them down. So the most common unit of measure is the degree. There are, as we know, 360 degrees in one complete rotation, 180 degrees in half a rotation, 90 degrees in 1/4 of a rotation, and so on. So degree measures can also be expressed using a decimal degree form, which we've seen, or a degree minute second form, and this will be kind of new to you. This is where each degree is subdivided into 60 minutes with a little apostrophe as the notation, and each minute into 60 seconds with what looks like a quotation mark right there. So in pre-cal in our class, we're going to just do things with the calculator, but for these first two, I am going to show you how we can do this by hand. So to convert between degree or decimal degree form and degree minute, that should be an S, second form, we're going to first take the angle 56.735 degrees, and we're going to convert that into degrees, minutes, and seconds. So the first thing we notice is that there are 56 full degrees, plus there are 735 thousandths of a degree. So we're going to take that part of the decimal and we're going to convert that into minutes. And we know that in every 1 degree, there are 60 minutes. So this way, our degrees are going to cancel, and I'll be left with minutes. So when I do that multiplication, I get 56 degrees plus, that turns out to be 44.1 minutes. So then what I want to do is I want to take the minutes and I want to convert those to seconds. So 0.1 minute, as I convert that to seconds, I know that in 1 minute, there are 60 seconds. So that gives me just 6 seconds. So as I convert, I have 56 degrees, 44 minutes, and 6 seconds. Okay, so that's how we would do it by hand, and here in a minute I'll show you how to do it, and I'll talk you through how to do it on the calculator. Okay, example 1b. Now we want to convert the angle 32 degrees, 5 minutes, and 28 seconds to decimal degree form. So we want to go back to having it look like example 1a, where it's all degree but some decimal. And we're going to round to the nearest thousandth place. So what we have is 32 degrees, 32 full degrees, plus then we have 5 minutes. Well, we're going to take those 5 minutes and we're going to convert those to degrees. And I know that there are 60 minutes in every 1 degree. Then I'm also going to take the 28 seconds, and I know that there are 3,600 seconds in 1 degree as well. So this way, I know that my units are counting down, or canceling out, minutes canceled, seconds canceled, and so when I do the math, I'm going to get 32 plus 5 divided by 60 is 0.083, and 28 divided by 3,600 is 0.008. And when I add those together, I get 32.091 degrees. And this would be decimal degree form. Okay, so when we are rounding in degree minute second form, if we have 30 minutes or more, we're going to round up. 29 minutes or less, we would round down or stay the same. If we have 30 seconds or more, we would round up. And if we have 29 seconds or less, we would stay at that same minute. So it's pretty typical rounding procedure when we're looking at degrees, minutes, and seconds. So decimal values after seconds round just like all decimals do. So once we get below seconds, we're just going to round like normal. Okay, so now as we do the work on the calculator, 329.125. So the first thing we want to do is you want to type this into the calculator, 329.125. And I wish I had a calculator to show you as I do this, so I hope this works for you guys. If not, just kind of play it again and try again. So 329.125, and then I want you to go to second, apps, which is going to activate angle. And if you see choice number 4, you'll see an arrow like this, and it says degree, minute, second, or DMS. So you want to choose 4 and hit enter. And when you do, on your screen, it's going to show you 329 degrees, 7 minutes, and 30 seconds. Just a few simple clicks. Okay, so hopefully that worked for you. Let's try going the other way. So we have 35 degrees, 12 minutes, and 7 seconds. So we want to convert this to decimal form. So we actually want to get this typed up on our screen. And once we get that typed exactly like it looks on our home screen, we can hit enter and it will convert for us. So the first thing we're going to do, you're going to type 35, then you're going to go to second, apps, which is again angle, and you're going to choose 1, which is the degree symbol, and it's going to put 35 degrees, and then you're going to type in 12, and then you'll go to again second, apps, which activates angle, and you're going to choose 2, and you'll see a little minute symbol, and then you'll have 35 degrees, 12 minutes. After that, this is really, really strange. You're going to type in the 7, and the second notation is actually going to be, not second, but it's going to be the green alpha key, and then the plus sign, which if you look in green or up above the plus sign to the right, you'll see the seconds, and that will give us 7 seconds. And then when we hit enter, it will make that degree, minute, second all into decimal degrees, which is 35.202 degrees. So, should be very easy to do that. All right, let's go to the other page. Now we're going to talk about arc length, which we've already visited a little bit. So arc length is the distance that we are traveling around a circle, and it's not necessarily all the way around the circle. In fact, most of the time what we're looking at, it's not all the way around. So this would be the arc length. In 4.2, we had a formula that related the central angle theta to its radius r and the length of the intercepted arc. And if you remember, we said that theta was equal to the ratio of the arc length over radius. So if we actually want to solve that so that we can find arc length, we would multiply both sides by radius, so we could say that s, or arc length, is equal to the radius times theta. And that's going to be very important. That's an important little formula for what we're about to work with in our applications. So using these same formulas, just manipulating them to solve for another variable, we have the arc length equal to r times theta. And one thing we want to remember is that theta is always measured in radians. And one thing that might help you to remember that, back in middle school, you learned the area of a circle was pi r squared. You never learned that it was 180 degrees r squared, right? So when we work with these formulas and circles, we always want to make sure that we're working in radians and in the pi mode. Okay, so to find the length of the intercepted arc in each circle with the given central angle measure and radius, in A, we have a radius of 5 and a theta value of pi over 4. So very simply, if we want this arc length, we have pi over 4, which is theta, times the radius of 5, so that would be 5 pi over 4. Now, because it's arc length, and 5 pi over 4 does not represent theta, it represents length of something, we want to turn that into a decimal. So go to your calculator, and we want to figure out and type in 5 pi divided by 4. And we will get that that's 3.9 centimeters. Okay? All right, let's look at letter B. So in letter B, we have 60 degrees and we have 2 inches, and we want this arc length. So I know that S is equal to the radius times theta, but 60 degrees is not acceptable. We need to change that. So if you don't already know that 60 degrees is pi over 3, we can use that unit conversion, pi over 180, to change it. So 60 degrees goes into 180 3 times, so we would get 2 times pi over 3, so our arc length is 2 pi over 3. And again, this is a length, this is a length, and we're in inches, so we want to do 2 times pi divided by 3, and we get a length of 2.1 inches when we round. Okay, now we're going to talk about areas of sectors. So now instead of the arc length, we want all of this inside. So the area of a sector of a circle with radius r and central angle theta is going to be area equals 1/2 theta r squared. Very similar to the area of a circle. And again, make sure that we always use radians when we plug in for theta. So we're going to find the area of this first sector. We have a radius of 3 centimeters and a theta of 7 pi over 8. So as we look at this one, we have area equal to 1/2. Theta is already in radians, so I don't need to change that. 7 pi over 8 times 3 squared. So as we do the math on that, we would get 7 pi over 16 times 9, or 63 pi over 16. And this is area, again, so we want to go and actually get a decimal value. 63 pi times, or divided by 16, will be 12.4 centimeters squared, because we are finding this area inside the circle. Okay, find the approximate area swept by the wiper blade shown if the total length of the windshield wiper mechanism is 26 inches. So what we want, we have the pivot point of the blade down here. The total length of this is 16, but the blade is 26. The blade itself is only 16. So what we have to find is just this area that is cleared by the windshield wiper. So this is a concept that we've learned for a long time and that we've used. To find this in here, we're going to take the area of the big sector. Let's see. Area of the big sector minus the area of the smaller sector. And then we'll have the difference. So the area of the big sector is going to be 1/2. If I have to turn 130 degrees into radians. So I'm going to multiply that by pi over 180. So that's going to be 13 pi over 18. So 13 pi over 18, and then the radius of the big sector is going to be all 26. So as I do that math, I'm going to get 766.9 for the area of the big sector. The small sector down below is going to be 1/2, again, 13 pi over 18. And the radius there is just 10, just this little piece. So 10 squared. So when we do the math on that, we get 113.4. And when I subtract those two areas, the difference of that is 653.5 square inches, and that will give us the area that is cleaned by the wiper blade. Okay. So linear and angular speed. So now as we look at the difference between linear and angular speed, first of all, we want to realize that whatever speed we always talk about, it's always compared to time. So any kind of speed will always be in comparison to time. So the formula for arc length, what we've looked at before, is going to be used alongside these two formulas. So we've learned that arc length is r times theta. So when we talk about an object moving along a circular path, we are talking about traveling around the circumference of a circle. And if we're talking about that speed, that is linear speed. And linear speed is a distance traveled. Moving forward or backward, it can be measured in inches, feet, yards, miles, meters. It has a linear distance. Now, the rate at which an object rotates about a fixed point. So if you pictured someone standing right there in the middle of the circle and following around and rotating like that dotted line rotates, that's angular speed, just rotating about a fixed point. So this is angular speed. And this is not something that we're going to measure with a distance. We're not going to measure angular speed with feet or inches because we're just simply turning. So angular speed is measured in revolutions. So whereas linear speed is measured in feet per second, something like that, angular speed will be measured in revolutions, maybe per minute, maybe per second, maybe per hour. But we're measuring theta, which is rotation. Okay, so looking at this example, for linear speed, if s is your arc length traveled by the object during time t, then the linear speed, which we're going to call v, is given by this, arc length divided by time. Now, one thing I referred to in class was that you probably remember distance equals rate times time. Well, this is the exact same formula, only we're going to use, they're just using different variables. Distance, guys, is really like your arc length around. That's really your s. Your speed or your rate, that's really your velocity, and time is still t. So if I take that d equals rt and turn it into distance being arc length, rate being represented as velocity, and I solve that for velocity, I have velocity or speed equaling arc length over time. So this is no different than the formula that you learned back in middle school or 9th grade. Okay, now angular speed, this is brand new. Theta is the angle of rotation in radians through which the object moves during time t. So it's just turning on a point, like turning a dial. So the angular speed formula for w, we have this really curvy w, is given by this, theta, turning over time, how theta changes over time. So linear speed is arc length changing over time, and angular speed is theta changing over time. So let's take a look at A. A and B both relate to the bicycle at the right and the tire, which is 30 inches in diameter. So A says, a bicycle messenger rides the bicycle shown. During one delivery, the tires rotate at a rate of 140 revolutions every minute. We want the angular speed of the tire in radians per minute. So if we want angular speed, we know that angular speed is the change in theta over time. Well, the time that they give me is 140 revolutions per 1 minute. So we have 1 minute that the change was recorded over the course of 1 minute. And we know that it's 140 revolutions, but that's not theta. Every 1 revolution is 2 pi. So if I have 140 revolutions, and every one of those is 2 pi, I'm going to multiply 140 by 2 pi, so my theta is 280 pi. That represents 140 times that we're going to go 2 pi radians. So now that I have 280 pi per minute, we're going to convert that to a decimal. 280 times pi gives me 879.6, again, radians per minute. Great. Okay, for part B, we need a little piece of information. In 1 mile, if you're not sure, there are 5,280 feet, and that's going to help with some of the conversions on the next example. So same bike tire, 30 inches in diameter. It says on part of the trip to the next delivery, the tire turns at a constant rate of 2.5 revolutions for every 1 second. Find the linear speed of the tire, but in miles per hour. So if they want linear speed, well, the formula for that is velocity equals s, or arc length, over time. Well, the other thing we send, and the time they give us is 1 second, 2.5 revolutions per second. So the time is just 1 second. But s, my arc length, well, that might be something I have to find, because I only have that it's 2.5 revolutions, but the radius has to be taken into consideration. So remember that arc length, as we talked about back up at the top, arc length is r times theta, right here. So if this is r theta, that's 15 as my radius, that's half of 30, 1 second. And now what is theta? Well, 2.5 revolutions. Each revolution is 2 pi, so my theta is 5 pi. So 15 times 5 pi gives me 75 pi radians, and now that is arc length. So that is in inches. That's not, our theta value is 5 pi, but multiplied times 15, that is our arc length or our distance, so I need a linear unit attached to it. So 75 pi inches per 1 second. Well, that would be great if they wanted inches per second. However, they wanted miles per hour. So we're going to have to do the conversion. So we have 75 pi inches in 1 second. I want to get all the way over here to miles per hour. So the first thing we want to change, you can change either one first. The first thing we'll change is maybe distance. I want to go from inches into miles. So to do that, I'm going to go through feet. Now, the pre-cal lesson ended with 75 pi inches per 1 second. Now, this is good old-fashioned conversion that we learned in Algebra 1, and maybe in our science classes as well. So 75 inches to get to miles. We're going to go through feet. I know there are 12 inches, which we want on the bottom, opposite the 75 pi inches, in every 1 foot. And then I'm going to put 5,280 feet on the bottom for every 1 mile. And this way my inches cancel, my feet cancel, and I am left with miles. Then I want to convert my time. I want to go from seconds to hours. Well, I know that there is 60 seconds in 1 minute, so that makes my seconds cancel, and that there are 60 minutes in 1 hour. So when you do the math on this, you're going to need to be careful in your calculator. I even canceled, you can type it all in as you want, 75 times pi times 60 times 60, divided by 12 times 5280. You'll get the same thing. I do a little canceling first. I do 12 becoming a 1, 60 becoming a 5, and then maybe 75 pi times 5 times 60, or 300. And then we're going to divide by 5280. You should get, no matter how you cancel, 13.4 miles per hour. Okay, so make sure you are diligent in practicing these applications. The math is not intensive, but the concepts take some practice.